All right, we are going to take a look now at calorimetry. Sorry, I was getting my microphone set up. So we're looking at topic 6.4, heat capacity and calorimetry. So we're just going to write through these, fill them in as we go together, and discuss our calculations. So have your calculator handy nearby so you've got that ready to go. All right, so calorimetry is the measurement of heat flow. That was also one of your vocabulary terms up here. So it is the process of measuring the amount of heat released or absorbed during a chemical reaction. It can also be during a physical change. Now, a calorimeter is a device used to determine the amount of heat transferred. So here's our calorimeter. So typically it's a polystyrene or styrofoam container due to its ability to insulate. So it keeps all the heat inside. So typically we've got 2 styrofoam cups. We double layer them. Excuse me. And inside we'll have something to stir with. We'll have a thermometer. We've got a cover and some water. So heat flow cannot be measured directly. We can't just say, oh, this is how much heat is gaining or losing. We don't have a device to measure heat. But what we can do is measure temperature, which relates to heat. So temperature we can measure before and after, and they are, sorry about that, used to calculate heat. And we're going to use the equation Q equals MC delta T, which we like to call Q equals MCAT. All right, so think about a little cat. Okay, there's my cat. MCAT. So that equation is one, hopefully, from Honors Chem that we remember, where Q is the heat, and it can be positive or negative, endo or exothermic. M is your mass in grams. C is called our specific heat. And it's measured in joules over grams degrees Celsius. So it's got a more complex unit. So I always think C is the complex unit. And then delta T, change in temperature. So this is our temp, and it is always temperature final minus temperature initial or starting, okay? In our last unit when we did changes in concentration, we did the, we saw this, A sub T minus A sub 0. Right? It was the final minus the starting. Anytime we're finding a change, we're doing final minus starting. So it's the same idea. So we're using this equation to help us find how much heat flows between substances, or how much heat is gained or lost by a substance. So to figure out what's going on, we have to define our system and our surroundings. So we need to know what chemicals or substances we're focusing on and then what's around it. So our system is typically going to be a chemical reaction. It could be a chemical dissolving. If you're making a solution, so we're dissolving something in water to make that aqueous solution. Or a third one it might be is like a metal. If we're trying to maybe find the specific heat of a metal, that's a common one because we can identify metals from their specific heats. And then the surroundings are going to typically be the water that the chemicals are dissolved or reacted in. So the solutions we're making, the bulk solution, really creates our surroundings, and then the actual breaking and forming of bonds where that reaction is occurring is what our system is. And those reactions can gain or lose energy and either give it or take it from the water and its other surroundings. The heat lost or gained by the water is equal to the heat lost or gained by the reaction. So for example, if our water is calculated to gain 568 joules of energy, it gained heat. This means that the reaction may be a reaction that's occurring there, an aqueous reaction, in the water, it transferred heat to the water, so the reaction is exothermic, so it lost 568 joules. They are the same amount or magnitude meaning size, but the opposite charge, or opposite sign, not charge, opposite sign. Okay, same amount, opposite sign, because our system, which is our reaction, is going to, in this case, lose energy, and it's going to go to the water that it's sitting in. Okay. So defining what our system and surroundings are can really help us see what's going on there. Now, we are going to flip our page. Extra one. So we're on page 6 now. And we're going to take a look at an example of using this equation and how this applies. So again, I would encourage, if you've got your materials from Honors Chem, maybe go back and review the Q equals MC delta T equation, kind of look at some of our examples we did, our problems we did. That's a good jumping off point, and then we're taking it to the next level here. So we can just use that equation to find one value. So if I want to find my heat of water, I can use the mass, specific heat, and change in temperature of water, and I can find Q. But we want to take it to another level and use that information of water to help us find out something else, maybe about a reaction or a metal or something, a chemical that's dissolving. So let's take a look at this situation. A 50.5 gram piece of aluminum, so that's a metal, is heated to 385 degrees Celsius and placed into the calorimeter over here. So we're taking a piece of metal at 385 degrees Celsius, and we're going to place it into our calorimeter. And it contains 200 milliliters of water at 22.5 degrees Celsius. So this is 200 milliliters. We've got 22.5 degrees Celsius. So those are both at different initial temperatures. Now, as we know, the energy of the water is going to eventually equal, the temperature of the water will eventually equal the temperature of the metal, right? They will eventually reach thermal equilibrium. So their final temperatures will be the same. Now, the highest temperature reached by the water is measured at 41.4. So it goes to 41.4 degrees Celsius. So we've got a final and a starting temperature for water. Now, we want to know the specific heat of aluminum. We want to know C, that variable C, for aluminum. So if we want to calculate that for aluminum, we would need the mass of aluminum, which we have, the amount of energy the aluminum gained or lost, and its change in temperature. Now, we don't have enough of that information right now to do that because we don't have the energy and we don't have its specific heat. We can't solve this. But we do have enough information about the water. So we're going to start by calculating the heat gained or lost by the water. So this is our first part. Q of water, and I like to label my Q. This little subscript is just labeling it which Q I'm talking about. So we need the mass of water. Now we've got 200 milliliters of water, and they give us some extra info here at the end. It says the density of water is 1 gram per milliliter. Okay, let's see what that does. If I have 200 milliliters and it's 1 gram per milliliter, then I have 200 grams. So they're equal to each other. My milliliters of water is equal to my grams of water. So we can use density to help us change between a volume and a mass. So I've got 200 and my sig figs 0.0 grams of water. And then I'm going to multiply that by the specific heat of water. So that is given here at the end of the equation, 4.18 joules per gram degrees Celsius. And I'm going to multiply that by the change in temperature of the water. Again, we got to be careful, make sure we're not just pulling out temperatures out of our setup because we've got 3 temperatures here. We need the ones of the water. This is why I like to kind of label a picture, kind of create my own little picture or list things with water or metal, kind of sort my information. So I've got final 41.4 minus starting 22.5 degrees Celsius. Now really quick, I'm going to look at some units. I've got grams and grams. I've got Celsius and Celsius that cancel. I'm left with joules, and joules are a measurement of energy. So my Q of my water, my energy gained or lost by the water. Now we can already see, we know water is at a lower temperature than the metal. So the energy is going to be going to the water from the metal. So my Q for water should be positive, right? Because it should be gaining energy from the metal. So I've got 200 times 4.18 times, and I'm going to put this part in parentheses, 41.4 minus 22.5, and close my parentheses. And we get a very large number. 158. We've got 3 sig figs, so 0, 0. I'm going to keep the zeros, but no decimal, joules of energy. So we can see it's positive. That's telling us that we gained water or gained heat in our water. Now, if I want to know how much heat was lost or gained by the metal, we use the law of conservation of energy, which means the energy lost by one thing had to be gained by the other. Well, here, our energy that was lost or gained by the water gives us our energy of our metal. We just flip the sign. So for number 2, our Q of our metal equals the same amount but opposite sign of our energy of our water, right? Because if the water gained it, got energy, it came from the metal. So metal is negative, water is positive. Now, step 3, our goal here is to find the specific heat of the metal. So now we have more information about the metal. We know its energy. We know Q for the metal. We have the metal's mass. We are looking for the specific heat, C, and the change in temperature we have. We have its initial, and we know it's ended at 41.4 as well. We know that because they have to end at the same temperature because of thermal equilibrium. So we are going to first, I'm going to write down my equation, and then I'm going to rearrange it. Now, I've seen a lot of mistakes happening lately in our class with rearranging equations, okay? Focus really hard right here. We've got Q of a metal. That's just a Q, okay? That's just a label on Q. I've got M times C times the change in temperature. If I want to solve for C, I need to move everything else away from C. If they're being multiplied, I need to do the opposite and divide them on both sides. That means this is your setup here. Your specific heat C is Q over M delta T. So my specific heat is my Q value, which I have from up here. Again, everything should apply to the metal now. This is all for the metal. Okay. My mass of my metal is 50.5 grams times my change in temperature of the metal. Excuse me. Final temperature, 41.4 minus 385. 385.0. The final minus the starting. Notice this is going to give me a negative number. We're going to have a negative over a negative. That's going to give us a positive. The only values that can be negative are your change in temperature or Q. C and mass are never negative. So my specific heat of the aluminum, because that's my metal, is, here we go, negative 15800 divided by, 50.5 times 41.4 minus 385.0. Close that parenthesis and the one on the bottom. And I get 0.91. Now let's check our sig figs. I got 3, I got 3, I got 3. So 911. My 5 bumps it up. Now my units. Okay, again, another thing I've been seeing lately is being really lazy about our units. If you include them here, then it tells you what your units are here. Notice I have joules, I have grams, and I have Celsius, and none of them cancel. So I keep them all, and I keep them where they are. Joules are on top, grams and Celsius are on the bottom. Specific heat units are joules per gram degree Celsius. So that is our answer. So here we're using water as the kind of as the surroundings to see how much energy transfers to it from a heated metal. And from that we can figure out the specific heat of metal. So the specific heat, its job, what it is how much energy, joules, it takes to heat a gram of a substance by 1 degree Celsius. So what this is saying is to heat up water, to take 1 little gram of water and heat it up 1 degree Celsius, it takes 4.18 joules. But if I compare that to aluminum only takes 0.911 joules of energy to heat 1 gram by 1 degree Celsius. So it's easier to heat up aluminum than it is water. Water is hard to heat up. It has one of the highest specific heats. Water does. It's one of the hardest substances to heat up. It takes a lot of energy into water to actually change its temperature. So that's our first example, how we can use our idea of thermal equilibrium, that things are going to reach the same final temperature, to figure out a missing piece of information, specific heat of a metal. This is a very common lab done in lots of chemistry classes. We did a more complex one last year instead of that, so we're going to take a look at that in a second. So now we are going to look at how do we deal with this kind of thing with a chemical reaction. What can we find from a chemical reaction? So a reaction we can't find a specific heat like a metal. Okay, that's not something that we have for a chemical reaction. But we can figure out how much heat or heat is gained or lost by a reaction, and how much heat is gained or lost per mole of the reaction. Okay, we can find the change in enthalpy. This is one way to find change in enthalpy. So let's take a look at a few notes here. So Q of our reaction. So RXN is a way to abbreviate reaction. It's very common. So our energy of our reaction is the heat lost or gained in the reaction that took place in the calorimeter. So in that container, in those styrofoam containers. It's in joules. And we use Q equals MC delta T, with M being the total mass of the reactants. So our chemicals reacting is going to be our mass of our reaction. Okay? And they're going to give energy or take energy from the solution that they're in. Okay? The solution they're in. So, the reaction is equal to the negative Q of our solution. So the water that they're dissolved in might gain energy, and then the reaction might give that energy off. We're going to look at that exchange there. The energy of the reaction is the opposite sign, but the same amount as the energy of the surrounding solution. So delta H for a reaction, the change in enthalpy of a reaction, is the heat gained or lost in the balanced chemical equation. We do that in kilojoules per mole. So we're going to have to do a little converting between joules and kilojoules. Remember, there are 1,000 joules in 1 kilojoule. Can help. And we calculate the delta H by taking Q of our reaction and dividing it by the moles of the reaction. So it's in kilojoules per mole. And we'll see how we can use it for a solution as well. So we are going to find Q and the moles, each of those pieces separately, then we'll divide them and get our final answer. So let's see how this looks. So the first thing we are going to do, let's read through our question or situation. These tend to be a little bit more lengthy setups to our questions. So you gotta bear with it and pull that information out and start dissecting it, okay? So in an insulated calorimeter, 100 milliliters of 1 molar NaOH and 100 milliliters of 1 molar HCl are mixed. So I'm mixing NaOH, and we're doing aqueous solutions on HCl. Okay, we've got a molarity and a volume. Equal molarity, equal volume. Okay, so this is going to go through a chemical reaction. Both solutions were originally at 24.6 degrees Celsius. So that's our temperature initial, okay, our starting temperature. After the reaction, the final temperature is 31.3, so T final. Assuming the solutions have a density of 1 gram per milliliter, so same density as water, and a specific heat of 4.18 joules per gram degree Celsius, specific heat of water. So this is our C value. Calculate the enthalpy change for the reaction, delta H. So we want to figure out what's going on here, okay? Now we can see that the temperature is rising, okay? Our temperature is rising. That means our solution is gaining energy, okay? Our water is gaining energy, right? That thermometer is down in the water. That means our reaction is giving off energy to the water, the solution that's surrounding it. So our reaction is breaking and forming bonds, and it's exothermic, it's giving off energy. Okay, so our reaction is going to be a negative value. Its delta H is going to be negative. Okay, so that's something you can look at your situation and think about what's happening and say, well, if my reaction is giving off energy, then my thermometer should go up in temperature. Because my thermometer, again, is part of the surroundings. So my reaction is giving energy to my thermometer, and therefore my reaction is negative or exothermic. Okay, so that's something to keep in mind and think about. So we're going to find the heat gained or lost by the water using the total mass of the solution. So each of our solutions each of our chemicals are dissolved in water. So most of this 100 milliliters is water. And we can take that total amount, so 200 milliliters, and like we saw in the previous one, the density is 1 gram per milliliter, so that's 200 grams. And we are going to find our Q value. So for number 1, we're going to find the heat gained or lost by our water, our solution, okay, our greater solution. So you can put water or you can put solution there. So we want the mass of all of that solution. So we've got 200.0. I'm going to keep all my sig figs. Keep your sig figs. Do not drop those zeros and those decimals because it throws you off at the end. Okay? So my mass times my specific heat, Q equals MC. This is my C. And that's the specific heat of water because, again, most of this is of water, times our change in temperature. Okay, our thermometer is saying we're going from 24.6 to 31.3. Final minus starting. It is not just big minus small. Okay, be careful with that. All right, let's check some units because I've written them down. Cancel my grams, cancel my Celsius. Okay, so my energy of my water is, calculate this out, 200 times 4.18 times 31.3 minus 24.6 in parentheses. All right, we get a big old values, 560. We got 4 significant figures there. Actually, we've got 3, so let's round that to 0. And that's joules of energy. So our water gained, because this is positive, 5,600 joules of energy, which means find the heat gained or lost by the reaction, flip the sign, and we're going to convert it to kilojoules. So my Q of my reaction is negative 5,600 joules of energy. Now, when we go to find delta H, we need it in kilojoules. So we're going to go ahead and convert that. So I just do a little kind of arrow thing here, and I say, okay, well, that's divided by 1,000, negative 5.6. We need 3 sig figs, so 0. Joules of energy. Oh, excuse me, kilojoules of energy. Whew. All right. So we've gotten our kilojoules. We've got one piece of these two pieces that we need to make this work. We need kilojoules per mole. So when you see something like this, I see my units. That's essentially an equation, right? It's telling me I need kilojoules, I need moles, and I need to divide them. So we got one piece, we need moles. So find the moles of our reactant, or one reactant, and convert to moles reaction. So we need to go from looking at one chemical to the total moles of the reaction. So let me show you how this works. We can see this is, we've got our two ions here, our ionic compounds. We're going to take, our hydrogen and hydroxide. Those are going to make water. This is an acid-base reaction, and sodium chloride. Okay, insides and outsides go together. And this is all 1-to-1, so it's a 1-to-1 mole ratio. So in this reaction, we're going to focus on one chemical so we can do some mole ratios here. Okay, so you can do NaOH or you can do HCl. Now, I've got a molarity and a volume. We love to give molarities and volumes. Molarity times liters gives us moles. So we're going to do 1 molar times my volume in liters, which is 0.1000 liters, and it stays the same. And I got 2 sig figs, so 0.10 moles of NaOH. All right. Now, to get to moles reaction, it says convert to mole reaction. So the way we do that, it's typically going to be a 1-to-1 ratio, but I'll just show you how you get there. In this reaction, NaOH has a coefficient of 1. So 1 mole of NaOH per mole of the whole reaction. Okay, for every one time the reaction occurs, I'm using 1 mole of NaOH. Typically, this is going to be 1-to-1. But if my coefficient was 2 here, I'd put a 2 on the bottom. If it was 7, I put a 7 on the bottom. The top is always 1. Okay, but this doesn't change my number. So I've got 0.10 moles reaction. Okay, so using our stoichiometry there, and I run out of paper here. So we're going to shimmy step 4 in here. Last part, actually, I'm going to do it up here where we got a little bit of space. So part 4, we want to calculate that delta H, that change in enthalpy of our reaction. Again, we basically have an equation here. It's a Q over the moles. We found our Q, negative 5.60 kilojoules over 0.10 moles reaction, and we're going to divide those. We are going to get a negative value. So negative 5.6 divided by 0.1 is going to give us negative 56 kilojoules per mole. So what does this mean? We've done all this work. What does it mean? Let's go back. My water gained 5,600 joules of energy when the reaction happened. So when these two things were mixed, my water gained energy, which means my reaction lost energy. Well, how much energy? Well, that energy is based on how much chemical is reacting. Well, I've got 0.1 moles reacting. So every time this reaction occurs, so for every 1 mole of reaction, so per reaction, I'm going to give off 56 kilojoules of energy. So that means in this reaction, I could also add as a product. Okay, we don't subtract in a reaction. We show it as a product, 56 kilojoules of energy. So when these react together, I make water, I make sodium chloride, and I make energy. All right, 56 kilojoules every time this reacts. Or we write delta H, and we make it negative to show it's exothermic. So the reaction gave the water energy. And that's what all of this comes down to. All right, we've got one more example, which your packet goes to this page 7 with this. That's not the proper page 7. So go to the extra page I gave you guys, put that in here, and then I'll explain what this second part is. All right, so we've got one more example. This one is for creating a solution, so dissolving something in water. So Q of our solution is the heat lost or gained in the dissolving process that took place in a calorimeter, again in joules. So our solution is going to be our water plus our solid, okay, because that is all the things that make the solution. So our mass is our water plus solid. Our specific heat is still just going to be of the water, because that's what bulk of the substance is, and then our change in temperature. So the energy of something dissolving is going to be negative of the solution. We flip that sign. The dissolving, bonds, intermolecular forces, breaking and forming, is the opposite sign of the bulk solution. All right, so we flip that sign. I feel like we're a little out of focus here. There we go. So we flip that sign. And then our delta H of the substance dissolving, so our change in enthalpy of that substance when it dissolves, is very similar to our reaction. It's in kilojoules per mole. Moles are calculated from the mass of the chemical being dissolved. So this part's a little more straightforward. You've got how much is being dissolved. We're going to change it to moles. We're going to divide. Okay. So similar to our reaction, we're going to read through this. We're going to see what's going on and start with energy lost or gained by our solution. So a 15-gram sample of ammonium nitrate is added or placed into the calorimeter containing 300 milliliters of water at 22.5 degrees Celsius. So I'm taking 15 grams of our solid and we're dropping it in. We've got 300 milliliters of water and it's at 22.5 degrees Celsius. The lowest temperature reached by the solution measured 9.2. So it went to 9.2 degrees Celsius. What is the enthalpy of the solution? Okay, that's interesting. We can see here our temperature dropped. Let's talk about what that means. If my temperature goes down, okay, I've got my water here, and I've got my solid. I'm just going to put solid so I don't have to write the whole chemical. Now, excuse me. As my solid dissolves, the temperature is dropping, which means my solid is pulling energy from all the surroundings in order to break those bonds or intermolecular forces in my solid. Okay, so my solid is bringing in some energy. It's taking it in. It's endothermic. So my final calculation down here should be positive. Okay, so let's see how that works out. We're going to start with our Q value and figure out the heat lost or gained by the solution, all the chemicals, right? Because the heat lost or gained is due to the water and the solid. So my Q of my solution is going to be my mass. Now we want the total mass. We want your grams and of your solid plus your milliliters of water. Now, they're in different units. But like we said, we can still use that density of water to assume this is 300 grams. So we've got 315 grams of chemicals, water plus solid. We're going to use our specific heat of water. I know that wasn't provided here. That's a little typo, but they would give that to you. Same as the others, 4.18 joules per gram degree Celsius. If you're ever given a different value that's not water, just use the one you're given. And our change in temperature. Now, our final is 9.2 and our starting is 22.5. Final minus starting. Again, not always big number minus small number. Watch those numbers. 3.15 times 4.18 times 9.2 minus 22.5. Notice how I'm putting that part in parentheses so it calculates it properly. All right, now my solution lost 175, so we got probably just 3 sig figs there, joules of energy, because our units here, we got grams canceling, Celsius canceling. So as we suspected, our water lost energy to our solid. Okay, so part 2, flip the sign, calculate kilojoules. So our energy for the chemical dissolving is going to be 175 joules, positive. We're going to go ahead and change that to kilojoules. So move that decimal over, divide by 1,000, 0.175 kilojoules of energy. Now, part 3, we want to figure out how many moles of chemical dissolved. Now, we have 15.00 grams. Our chemical is ammonium nitrate. So we got to use our molar mass here and calculate. All right. Let's see. We've got 2 nitrogens, and their mass is 14.01, plus 4 hydrogens, so 4.04. Plus 3 times oxygen, which is 16, 80.06 grams per mole. So 15 divided by 80.06, and we get 0.18. Let's see, we got 4 sig figs, so 1874 moles of our chemical. All right, just like in our reaction, we're trying to find delta H. We want it in kilojoules per mole. Again, that's just like having an equation. It's telling you need kilojoules, you need moles, and you need to divide them. So we've got kilojoules. So delta H equals 0.175 kilojoules over 0.1874 moles. You can see that's close to 1, little less. 0.175 divided by 0.1874. 3 significant figures, delta H equals 0.933 kilojoules per mole. Now you notice here we get a positive value. We said earlier it was endothermic. That fits very nicely. We tracked our stuff. So your change in temperature helps you determine who's gaining, who's losing, what your sign is, and keeping track of those signs. Okay? So these are similar problems, but they are not the same. When we're doing the first one and finding our specific heat of our metal, we end up kind of using the Q equation twice. But in reactions or creating solutions, we've got chemicals involved. We are going to use Q to find our energy, flip that sign, and then find our delta H. So this is the energy to dissolve. So if I wanted to write a reaction for this, and this is, I believe, in a few of your practice problems as well. I can take my solid, and to write a let's call it a chemical reaction for this, we're dissolving it in water. We do not add water. Okay, we just show it dissolving. So this breaks apart into aqueous ions. And that is our chemical reaction, okay? It's the solid breaking apart. The water is where we say aqueous. So we don't add water, we're not reacting it with water, we're just separating the ions in water, okay? So if you're asked to write a reaction, which I believe some of your practice has you do, that's what we want to do for something dissolving. Now, if it's a chemical reaction and you've got multiple things, write your chemical reaction. Now, in your notes, I have added some optional additional examples. So if you're like, I'm doing okay, I'm kind of getting this, but maybe I need to see a couple more, or maybe you start practice and then you realize you need to see some more, I've added a couple examples. So these are from Dr. Dina Leggett. She is a great chemistry teacher. She does some of the AP Chem videos on the College Board site. And so these are linked on my playlist, and I have copy and pasted her examples in here. So there's the first video, it says calorimetry, magnesium plus hydrochloric, so it'll have that and then a metal. This one's nice because it shows experimental data, so how do we pull those numbers? And then in your packet, the real page 8, okay, so that goes into the video number 2 on calorimetry, NaOH plus water. So this is another dissolving problem, and she does a nice example of of a dissolving problem. So I've got that there for you. So those are optional. You don't have to do them, but they are available to you. If you're good, you can jump to the practice on page 9 in your packet, 6.4 practice, okay? Make sure you're reading those questions carefully and thinking about what are we doing. So like this one's talking about a copper bar is heated and placed into water. So we're going to be dealing with water here and just heating that metal up. Here we've got a reaction occurring. So we're mixing two chemicals. So we want to follow that. So just read your your problems and think through them carefully, okay? All right, guys. Let me know if you have questions, what questions you have, where you're getting stuck, and I would be glad to help you. Sorry, the video's a little long, but the examples are kind of long. All right, bye, guys.